7 is vibration isolation. So let me show you with this one. Isolation with the base motion. So if your base is moving up and down, how do you isolate the motion of the base? So this is an example of a base which is moving with a y displacement, and the mass is also moving. Oh, sorry about that. So this base is moving, and um, we want to reduce the transmissibility. So what is the transmissibility? So if I ask you, can you draw this mass? Can you take this mass and derive the draw the free body diagram? So you will do like this. So if this mass is moving with this displacement x, so when this mass moves upward, okay, then the force of the damper would be negative c x dot minus y dot, and the force due to the spring would be negative k x minus y. Then you apply the Newton's second law, all the forces, this is equal to mass times acceleration, and then this is the acceleration, and then this is force number one. So let's write down force with the damper x dot minus y dot minus k. And if I bring x on the left hand side, um, then you will see cx dot plus kx on the left hand side, and the right hand side would stay like negative. Negative becomes positive, so you don't need to write down positive, just write on cy double cy dot plus ky. So then our transform, after you take the Laplace transform, do the rearrangement of everything, so you will get this as ms square plus cs plus k, and in the numerator you will get cs plus k. Then now this is known as, what is this known? This is known as the transfer function. When you have the displacement transmissibility, that tells me that suppose this y is moving like 1 centimeter up. How much is this mass moving? Is it like 1 centimeter or 0.5 centimeter? So this is known as the transmissibility, that how much displacement from the base excitation has been transmitted to the mass displacement. So this is known as so now we have to reduce it to a zeta form. So let me show you the zeta form here, so that you will not you will see such questions, so you would not be able, you can find out the transmissibility using this formula. So this can be reduced, the same form can be reduced in this form. So this is known as the displacement transmissibility, and this is equation number 7.4-6. This is equation number 7.4-6. Now another thing which you can see, this is a force, this is a force due to the spring, this is a force due to the damper. So I can write down that, suppose in other hand, if this mass is moving, then it generates some force to the foundation. So there is another transfer function, how much force is being transmitted to the foundation. So let me show you, this equation here. Another transfer function, you can write down the force transmissibility, that from this, like if the machine, suppose this mass is like a laundry machine, and this is rotating, and the base starts experiencing a force from the transmitters. So so for ft over k. So this is the transmissibility. So now let's do this problem. Let's do one. Sorry, one more thing I want to show you, that you can write down in this form that this is what is this whole thing? This whole thing is x over y. So I can replace this by x over y. So then I can simplify the force transmissibility in the form of the displacement x. Okay, let's do one problem. Let's do one problem. Um, Before I do the problem, I want to show you the table. I want to show you one table here. So the table is this one. Now I want to show you one question here. This is the question. Let us solve this question together. A 15 kilogram instrument is used to is to be used on a factory floor. So the factory floor that is vibrating with this RPM. And the amplitude is due to the nearby equipment. So 3 millimeter. And in meters, I can write down into 10 to the negative 3 meter. The instrument can withstand an acceleration no greater than 4g. So the acceleration is 4g. And you remember the displacement and so how do you refine? You remember I gave you a long time ago. I explained you that if this is a sinusoidal motion, which is a vibratory system, so you can find out the velocity, the time derivative of this function, and you can find second time derivative, which is this function. And now what is this a sine omega t? A sine omega t and a sine omega t is again x. And if you take the displacement, so I can write down the displacement. So you see, so this term I can convert x, the relationship between x and displacement and acceleration can be written like this. So the question is, assuming the damping ratio. So we have a damping ratio. Let me write down here the damping ratio 0.02. Compute the required stiffness of an isolator, that the maximum deflection of the isolator. So we have to find out the maximum displacement of the isolator and the maximum deflection. So we have to find out the stiffness of an isolator. So what is my forcing frequency? So let me show you this formula. This formula, I can write down this formula here. And do we have zeta? Yes, we do have zeta, which is equal to 0.02, zero point 0. And do we have omega? So what is R? R is equal to omega or omega. And what is omega? Omega equals to 2 pi n over 60, which is the vibration of the floor, and the amplitude is given. So vibration of the floor, so I can write down here omega as 2 pi over 60 times the n is 3500. So if you calculate this, what do you guys get for this one? So let me show you the way you will solve this one. So I can write down. And the displacement of the base is 3 millimeters. So can I write down like this? X over y equals to, from here, can I write, let me write down here. From here, I can write down x equals to y and y is given as 3 into 10 to the negative 3. Now, what is this? Can I write down x acceleration in terms of omega square x? So what is x? X is nothing but this. So can I write down acceleration on the left hand side as omega square? Whatever I wrote down here, I just copy and paste it over here. Can I write down like this? according to this formula, because x is nothing but y times this factor. So y is given, omega square is also given. This is omega, you just have to take the square. So I can write down what is x double dot. X double dot is 4 times g. So let me write down the whole equation. 4 times 9.81. Actually, this is, sorry about this, this is a square of the whole. Yeah, this term has a full square, so this is full square, and divided by, so this is one equation, one unknown. Okay guys, so how can you find out r square from here? So if you do the math here, let me show you. Let me show you the equation which you get when you go home. Try to um, do the algebra. That will give you r square equals to 11.36, and another r square is negative 9.19. So use this positive value and plug it in k. So what is my r? Omega r square equals to omega square over omega n square. So from here, so what is my k value? So I can write down omega square, which is 350 pi over 3 whole square. So if you manipulate it, so let me, this is equal to 11.36. So I can write down, I'm in the numerator, this I'm going to, so k equals to 350 pi over 3 whole square. Fifteen kg. So if you solve for this, so this is my, this is equal to 15 kg. So k equals to 1.77 into 10 to the 5 newtons per meter. So you want to find out the ratio r square from this displacement transmissibility that gave you this answer. Let me solve one more problem for you that will clear another concept. I'm gonna open another homework for this chapter 7. Please note down this. So let us solve this problem. It says the mass of an instrument is 50 kg, is used on a table that vibrates due to the nearby. So this is like a, I would say this is like a table, and let me see if the mass, this is moving with a y displacement, this is moving with a x displacement. And now let us see the the principal frequency component is n. Omega equals to 2 pi n over. Okay, the mass is 50 kilograms, forcing frequency is 50 pi. Determine whether the isolator A or B, whose deflection curves are given in 7.44, can be used. Each of the corner of the instrument. So instrument has four corners. Four corners may be like one, two, three, four, and determine instrument as so that the no more than 25% of the table motion. So transmissibility, which is it is 0.25, like 25% maximum displacement can be transmitted to the instrument. So now the question states determine how each added mass is required, if any. So let's do this question. So I would say first you find out what is this displacement transmissibility formula. So I will start from here. That is equal to 0.25. So choosing an isolator A. So let me show you what is isolator A and B. So isolator A is this line, isolator B is this line. Assuming the damping ratio is this, you can assume from equation 4, but this is my equation 7.4 dash 6. So if you solve for this now, this will give you r raised to power 4 negative 2.02 r square minus 15. So r square equals to 5.015, another r square equals 2.394. So you can select r square either 5 or 2.39. So the natural frequency of isolated system would be equals to 50 pi over r. I'm sorry, this is not R square. This is R. So what is R equals to if you plug it in? So let me write down over here. 50 times pi divided by, I got the natural frequency is 65.7 radians per second. And the static deflection from this natural frequency, if you know the natural frequency, the static deflection is this formula. How do you get this formula? It's not difficult. You know that if there is a mass and this is a static deflection, so if you leave this mass, it is balanced by so x. So I can write down g mg equals to k times delta. Agree? So delta equals to what? G mg over k, or g over k over m, which is equal to g over omega n square. So the delta is, if you plug in this value, which is g, which is 9.81, and omega n, it is 65.72 whole square. So if you solve for this, 0.00, 2.27, I would say like 2.27 millimeter is a static deflection. So because we are using four isolators, the static load on each isolator due to the weight of the instrument will be divided by 4. So I can write down here. So to suppose this is my instrument, it has 4 isolator. So the static load would be divided by 4. So I can write down here. So each instrument, I will say 50 times g, which is 50 is the mass. 50 is the mass, and it is supported by the 4 corners of the instrument. So that no more. So 4 corners, 50 divided 50, so 4. So mass would be equal to 122.6 Newton at each corner. So the graph A shows that the isolator deflected at a load of 122.6, about this much. It's approximately 4.5, 4.5 millimeter deflection. The safe static load for isolator, however, 150 newtons. So we should mount the instrument on a block weighing 4 times 150 minus 122.6 equals to 110 newtons. So this is 4.5. Okay guys, so that's how we find this force transmissibility, the displacement transmissibility. So what I'm gonna show you here, so the safe load, static load for this isolator, K times delta is 150 Newton. So I would say 110. So we should mount the instrument on a block weighing for 150 minus 122.6. Let me show you this one. So the safe static load isolator is 150, correct? According to the graph. As per graph, it should be 150. So, but our load is at each location is 122.6, correct? So, so we should mount the instrument on a block that should weigh about 150 minus 122.6, so 110 newtons. That's how you find out the isolator between the block and the table. Place the isolator between the block and the table. Okay, now let's do one more problem. So this is an example. A printed circuit board may be sensitive to vibration because vibration can loosen the solder joints attaching the components such as resistors. So this is a PCB. PCB is like a fixed beam, and if you have a fixed beam, this end is also grounded, this end is also grounded, it has a mass, and effective mass is, so okay, let me draw this a little bit three-dimensional. If this is three-dimension, because it says the PCB supported by the chassis. The chassis is vibrating a motor. This chassis is vibrating motor. This is a motor, and the transmissibility from this motor goes into the PCB circuit board, which, I'm sorry, this is X. This is not M. This is my transmitted displacement to the printed circuit board when the chassis is vibrating at a certain frequency, which is 60 hertz. So the forcing frequency is 2 pi f, which is 60. So the board is 1.6 meters. So this is thick. How thick it is? It is 1.6 millimeter thick and 178 178 millimeter wide. How long is it? It is 200 millimeter. Oh, and this is very useful information for finding out the moment of inertia, which is WH cube over 12. And if I go back to the beginning of the lecture, we have to find out the stiffness. Okay, stiffness of the fixed beam, it is this formula, and effective mass is about 0.37 of the rho al. Rho al is nothing but the mass. You can also assume this is point five of the mass, which is the effective mass of the fixed beam. So let me show you that K equal EI K. Let me show you that the stiffness of the circuit board is, I can write here, 192 EI or L cubed. Let me make sure this is 192. Yeah, this is the same thing which I found it over here. So let me write down the value W in the form of WH cubed. So I can write down 192 E over L cubed W times H cubed over 12. Three fours are 12, three six are 18, three fours are 12, four ones are 4, four ones are 4, 4, 6 are 24. So 16 WH cube over L cubed. This is also the stiffness of the formula for the fixed beam. So the question is, determine the stiffness and the natural frequency. Compute the displacement transmissibility of the if the chassis vibrates due to the motor unbalance. The board is made from epoxy glass from E is also given. Did I tell you this thing? E, I forgot. Now it is E is there. So let me write down from this formula 16 times E is 1.38 into 10 to the power 10. Okay, W is how much? 178. I would write down meters, 0.178 meters, and H is 0.006016 cubed over L. L is 200, so I'm going to write down meters, 0.2 power 3. Agreed? So if you solve for this, the K value of this circuit board is 2. Okay, the K value has been found. Now you have to find out the natural frequency. So natural frequency is, the formula is square root K over mass. Here is the effective mass. If you see the formula for the effective mass is zero point 0.4 rho times. So the the mass is zero point 0.4. And this the mass of this circuit board is 0.45. So but I would write down the effective mass, which is 0.45 times zero point 0.5 or divided by 2. It's almost 0.5, so you don't need to worry. So if the mass is given, K is given, mass is given, can I write down the natural frequency? So let's do this math together. So I can write down square root K, which is 2.012 power 4 divided by 0.225. It's about 299 radians per second. So this is the natural frequency of this printed circuit board, which is having this radians per second. And now it says find the displacement transmissibility. So it does not have any zeta value. So zeta is assumed to be 0. And I know that the displacement transmissibility is this formula. I'm going to grab this formula. Okay. And I'm going to show you that what is this transmissibility. So this is also known as the displacement transmissibility. If this is 0, this is 0. So you're left with 1 over, I would say keep it in mode 1 minus r square as a absolute value. So what is that? R value is nothing but omega over omega n. What is my omega? The forcing frequency is 60 hertz, which is 2 pi f 60 hertz. Omega in is 299, 299. So what is r equals to 1.26? You plug in this number over here and find out the, so let's do this. Let's do this together. So I'm gonna write down. So 0.26 power negative 1. Oh, I'm sorry. This is omega squared. Sorry. This is R. So I will say 0.26. No, I'm sorry, the parameter is, sorry about this. So this is my R square. So let's do this slowly. 1 minus 1.26 whole square equals to, so equals to transmissibility. Yeah, I know why. Don't worry about the negative sign because we are taking the mod value. So it is 1.7%. Like what does it mean? Sorry, it's in decimal. So what it means that it is, if it is in decimal, so it is about 1.701, means that means 170% transmissibility. So y, so x, sorry, x over y. So x is equal to 1.7 times y. Do you understand this question? If you understand this question, please type in yes in the chat box. Christian says yes. Khan says yes. That's good. Okay, let's do another. Caleb says yes. Let's do another problem. Regarding this problem, I want to continue. What is the vibration isolator? How do you isolate this 1.7, which is about quite high? So how do you reduce this vibration to 20% using an isolator? So the next question, which is related to this question, about 169%. So how are you going to reduce it to 20% transmissibility using an isolator as shown in the figure 7.4-6? So I'm going to show you. So now you will place this isolator, and what is the C value and what is the K value. So let's do the math here. I want to show you. So we know that whatever the forcing frequency is, so our transmissibility is now zero point 0.2. So now let's see what is our transmissibility now. 20%. Required transmissibility 20%, which is equal to zero point 0.2. So I will say x over y equals to 0.2, y or x over y equals to, so I'm going to write down this formula again here. But here I want to show you that transmissibility is given, and zeta, the standard rubber isolator, typically has a damping ratio between 0.02 to zero point 0.1. So zeta ranges from 0.02. This is, sorry, this is 0.02. Point. So let us choose our isolator, vibration isolator, which is having a damping ratio of 0.02. Now another thing which you have seen here, that the mass, chassis mass is 1/10 of the mass of the, we are told that the chassis mass is 1/10 the mass of the PCB. So the total mass as a rigid body. 0.45. Okay, now zeta, let us assume the lowest value of zeta for vibration isolator, zero point zero 0.02, and transmissibility equals to 0.02. 20% is, sorry, it is zero point 0.2. It is not point. I was confused with the zeta value. So this is 0.2. Agreed. So now from the equation 7.46, this equation, from this equation, what what do you get for R value? So let me grab this equation here. That is equal to zero point 0.2. If you plug in R from this equation, you should get R equals 2.4634. And that will give you the required value of the stiffness K2. Because remember this omega, which is now 377. So R square equals to omega square over omega n square. Omega n square, this is 377, which is our, how do you get 377? Look, this is vibrating at 60 hertz. 60 hertz means 377. Agreed? So how do you write down? Let me show you 2 pi f. So I can write down here 2 times pi times 60. About 377 radians per second. This is the forcing frequency. So now this is our forcing frequency. Can you find out omega n square from here when you know R from this transmissibility ratio equation? So of course you can find it out. And remember that the omega n is the natural frequency of the isolator. Omega 2 equals to K2 over M. So isolate, I would consider this as a, so effective mass, which is omega n. So let me write down here, omega n square is equal to omega square over R square. So this is my scale of the natural frequency. Now from here, what is omega n square equals to? K2 over M. That means stiffness of the vibration isolator is equal to m omega n square. M is equal to 0.495 as a rigid body. 0.495. Mm. So let me do this math here. So if I grab this value here, multiply by 0.495. So 11,625 newtons per meter. 11,600. So or 1.1625 into 10 to the power 4 Newton per meter. This is my stiffness of the vibration. With this stiffness and with this mass, I can reduce this transmissibility to 20%. And what is C? How do you calculate C value? We have still not completed our question. We have to find out what is C. How do you get C? And you guys know that C equals to, so zeta equals to C over CC, actual damping over the critical damping, C over 2 m omega n. which is the formula for the critical damping. I can rearrange everything to m square root k over m. I can rewrite here like this, square root 2 square root mk. Okay, now, so we need to find out what is my c. So this is k2 is given, m is given, so c equals to 2 zeta square root mk2. So 2 times zeta point zero 0.02 square root 0.495, k2 is 11,000, 1.159 into 10 to the power. So let's do this math together. If you open your calculator, I got 3.03 Newton second per meter. This is my actual damping of this vibration isolator. When you have this damping system, this is Newton second per meter. When you have this vibration isolator, then you would be able to reduce this transmissibility to 20%. Please type in the chat box if you have understood this question. If not, let me explain you if you haven't understood this question. Christian says yes. Conley says yes. Caleb says yes. That's good. So when you go home, practice another problem. So you would do this problem here. So let me just show you this is, I'm gonna stop the recording. So I want to